coming to the realization of your digital filters, yes, what we have done in the previous classes is we have designed the digital filters. Designing of your digital filters, of course, we were designed the impulse invariance response type of your filters, infinite impulse response type of your filters. That is, in those type of filters, when we are designing, we are using a transformation technique also. One is your bilinear transformation technique, and the other one is your impulse invariance response transformation techniques. And now in this particular chapter, we are trying to realize this filters. Realization of your filters is nothing but what we are trying in bringing the transfer function, what we have designed in the earlier classes, that is the transfer function what we have got, that is maybe in your h of z format. And that particular transfer function, we are trying to bring it down in the form of what? We are trying to bring it down in the form of the structures. Okay, and that particular structure is nothing but your realization. That is, we are trying to bring it down in a form of a structures. Okay, so and that particular structures, there are different types of structures for your realization of your IAR digital filters. That is, we have a direct form 1 structure, we have a direct form 2 structures, we have a parallel structures, and we have cascade structures. We have some 4 different types of your structures, and those different 4 structures we will try to discuss. Okay, yes. Coming into the first structure, that is what we have here is your direct form 1 structures. What is this direct form 1 structure? In this particular direct form 1 structure, that is the given transfer function, the transfer function which is consisting of course in the form of what we have a poles and we have a zeros, of course. Okay, and those zeros and poles we are trying to represent in a form of what we have called it as a structure, and that particular structure will be comprising of the components, the digital components. It may be the digital components, or what are the digital components will be using will be, it may be your time delay element, calling it as a z inverse, what we call it as a memory element. Then we have summing points or summers, that is we can also call it as an adders. Okay, then we have a multipliers. Okay, so those are the simple components which we people will be using to get it down in the form of a structure. Okay, uh, yes.
Yes, sir.
Okay, getting back into the structures, that is, of course, we are trying to bring down the structures. In the direct form structures, that is what we are trying to do here is, yeah, the first thing is I've just taken a simple example, that is a transfer function. And this particular transfer function, which is there in your Ganesh Rao textbook, you can refer it there also. Okay. Yes, what is the transfer function? It has been given, that is h of z is equal to, you can just listen now and you can just try to do it later. Okay, what is the h of z? H of z is equal to 8 into z cube minus 4z square plus 11z minus 2 divided by your denominator z minus 1 by 4 entire thing into z square minus z plus 1 by 2. Of course, the denominator, we have just multiplied the denominator and we got an order of the transfer function as a third order transfer function. We can see that is the order of the transfer function. What we got is a third order function. Okay, so and this particular transfer function has been represented, that is in a form of h of z. Of course, by simplifying the denominator, we'll get in a transfer function equation as 8z cube minus 4z square plus 11z minus 2 divided by z cube minus 5 by 4 z square plus 3 by 4 z minus 1 by 8. Okay, here we can see that the order of the given transfer function, now it is a third order transfer function, that is order is 3. So what I'm trying to do here is, that is I'm trying to divide both the numerator and the denominator by the highest order. The highest order, it is third order 3. So I'm dividing it by what? Z cube itself. So if I divide the numerator and the denominator both by z cube, so what is the left out equation I'll be having? My left out equation will be 8 minus 4 into z to the power of minus 1. How we got z to the power of minus 1 here? That is, we can see here, that is 4z square is been completely divided by what? By z cube. Okay, so what will happen? It will become 4 divided by z. This 4 divided by z is nothing but 4 into z to the power of minus 1. I can write as 4 into z to the power of minus 1. Similarly, we have 11z, which is divided by what? Z cube. That is nothing but 1. It is 11 divided by z to the power z square. It will be, that is nothing but, I can write as 11 into z to the power of minus 2. Similarly, we will get what? 2 minus 2 into z to the power of minus 3. And of course, in the denominator, we'll be getting as 1 minus 5 by 4 z to the power of minus 1 plus 3 by 4 z to the power of minus 2 and minus 1 by 8 z to the power of minus 3. This is the transfer function what we get, that is after dividing the numerator and the denominator by the highest degree. What is the next thing we have to do? That is, of course, this transfer function h of z is nothing but I can write down in a form of what? The output by the input, that is nothing but what? Y of z by x of z, where output y of z and input is my x of z. So the same transfer function h of z I have written as y of z divided by x of z, which is equal to the obtained transfer function, that is the complete transfer function what we have obtained in the case, in this particular case, that is 8 minus 4z z to the power minus 1, yes, etc. What we are done now in the next step, of course, we are trying to cross multiply both the things. That is what we are trying to do, is cross multiplying both the things. That is nothing but we are trying to cross multiply by y of z into 1 minus 5 by 4 z inverse plus 3 by 4 z to the power minus 2 minus 1 by a z to the power minus 3 and x of z into the numerator term, that is 8 minus 4 z inverse plus 11 z to the power of minus 2 and minus 2 z to the power of minus 3. And of course, we have written the same thing here in this particular transfer function in the form of an equation, okay, which we can see here. That is, yes, this is the transfer function what we or the equation what we get. Yes, what is the next step? I'm just trying to take the inverse z transform of it. If I try to take an inverse z transform of it, what do we get? In place of z, I'm trying to replace with the n term. Okay, so taking inverse z transform, of course, I can write the same expression as y of n minus by 5 by 4. Of course, z to the power of minus 1, I can replace with what? Y of n minus 1. And z to the power of minus 2, I can replace what? With y of n minus 2. Similarly, z to the power of minus 3 can be replaced as y of n minus 3. Okay, so the entire thing is been replacing with the n term. Okay, so we'll get an equation which I am trying to equate with the y of n. So the final expression what we're getting in terms of y of n is y of n is equal to 5 by 4 y of n minus 1 minus 3 by 4 y of n minus 2 and of course plus 1 by 8 y of n minus 3 plus 8x and 1. Yes, of course, I have brought my y term to the right hand side and keeping my what 8x and that is x terms as it is, the final expression will be this is the expression what we get. Then once we get this particular expression, the next step is the plotting. And this is the important step here, the plotting of your transfer function. How to plot this particular transfer function? In a form of a direct form, one structure. Okay, so I am trying to relate the transfer function, that is the expression, with two terms. One is the output, my output is y of n, the input is my x of n. That is, first write down one complete straight line. I'm just trying to rewrite in terms of steps. Okay, so the first thing is write down this particular straight line, that is from what we have an expression which is relating with respect to y of n in terms of that is in terms of y of n and x of n itself. Okay, yes, so I've just written a straight line here. The next thing is, of course, we can see my what is my y of n. Y of n is given by 5 by 4 of y of n minus 1, then minus 3 by 4 of n minus 2 plus 1 by 8 of n minus 3. So how many delay elements is required in terms of for my y of n? Okay, so we need 3 delay elements. We can see that is n minus 1, n minus 2 and n minus 3. So we need 3 delay elements. So z to the power of minus 1 is the first delay element, then z to the power of one more delay element, z to the power of minus 1, then one more delay element which is z to the power of minus 1. 3 delay elements has been taken here. Okay, yes, we can see here. So y of n, which is given by what? 5 by 4. Okay, so 5 by 4, which has to be multiplied with my delay element, that is for y of n minus 1. Here it is y of n minus 1. So I'm multiplying with the what? The multiplier, the value, that is 5 by 4 into my y of n minus 1, that is nothing but z inverse. So we can see here, so this is 5 by 4 into z to the power of minus 1. So the first step what I do is, with a adder or a summing point, I try to draw this. Okay, so we have 5 by 4 into y into n minus 1. Okay, I can just add one summing point here also, here. Okay, no problem, you can just add one summing point. This dot, the is combining my the first delay element with the second delay element can be done with one more summing point here. I can just add one more summing point here also, no problem. Okay, what is the next step? Here we can see my y of n is given by minus 3 by 4 into y of n minus 2, that is the second delay element. So this is my y of n minus 1, and second one here, one more delay element. After this delay element, my answer will be what? Y of n minus 2, and this has to be multiplied with what? Minus 3 by 4. So this is minus 3 by 4 into y of n minus 2. Okay, so minus 3 by 4 into y of n minus 2 with the summing point connecting to the same summing points here. Okay, next it is 1 by 8, of course, which is plus over here. So plus into 1 by 8 into y of n minus 3. Okay, that we are trying to write in terms of a y of n. Okay, coming into the same expression here, of course my y of n is also related with the terms x of n also, which we can see here, which is 8 into x of n. Where is my x of n? Here we have an x of n which has to be multiplied by an 8 term, 8 here. Okay, so it is 8 into x of n. Okay, then what is the next term we have? We have another delay element, that is x of n minus 1, that is x of n minus 1. Of course, this is my x of n minus 1 here, which is with the delay element z inverse. Okay, so we have another 3 delay elements which is necessary here also, that is x of n minus 1, n minus 2 and n minus 3. Okay, so we need 3 delay elements here also. Okay, so next, writing down the first delay element, the answer here will be, it will be x of n minus 1. The output after this delay element will be x of n minus 1. The output after the second delay element will be x of n minus 2, and the output, that is the at the third delay element, will be x of n minus 3 here. Okay, so what will be the answer now? That is minus 4 into x of n minus 1. So I'm multiplying the first delay element with your minus 4. So this will become minus 4 into x of n minus 1. I can just put one summing point here also. I can put a summing point here. I can put a summing point here. Okay, so I can put one more summing point. Okay, here also I can put one more summing point. Okay, yes, so it is minus 4 into x of n minus 1, then plus 11 into x of n minus 2, and minus 2 into x of n minus 3. If you just see, once we draw this direct form one structure, okay, the thing is, we have actually, if you see here, the number of delay elements required here for a third order transfer function, the number of delay elements required is getting doubled. That is nothing but if the order of the filter is 3, that is if the order of the filter what we have obtained is 3, and the number of delay elements is required is twice of the n. So we can say that in the direct form 1 structure, the number of delay elements required filter. Okay, so twice of the order of the filter. And if you see that is my direct form 1 structure, we have in the direct form 1 structure both poles and as well as been zeros is been plotted in a separate form. Okay, or else I can just draw this complete structure looking into the directly from the transfer function also. That is what we call it as a shortcut method. Okay, in the shortcut method what I can do is I can just draw the complete structure directly looking into the transfer function, but it may not be happening for almost all the type of your transfer function, but you may end up with what we call it as the mistakes also. So better, instead of going for a shortcut method, I can better to go with your what is called as a procedure, that is finding out your expression in terms of a y of n. But if I still want to do in a shortcut method, of course I can do in a shortcut method. That is what we have to do here is the first thing is plot the line, that is x of n, from x of n to my y of n. Then I have to check the number of delay elements required in the poles, and as well as I have to check the number of delay elements required in my zeros. Okay, looking into the poles and the zeros, the number of delay elements, we can see it is 3 required, that is depending upon the order. So we need 6 delay elements totally, 3 for your poles and 3 for your zeros. Okay, then looking into the zeros, if you see the zeros, actually the sign terms, okay, that is, this is a transfer function what we have obtained, that is h of s given by 8 minus 4 z inverse plus 11 into z to the power of minus 2 minus 2 into z to the power of minus cube, that is this is the transfer function. Okay, so looking into this particular transfer function, I can just directly try to write the what structure here. Okay, so looking into this, I am trying to write here, you can see here it is 8 as it is 8, we can write down from here, that is from the x of n towards the y of n. Then we have a minus 4 with the one delay element. Yes, minus 4 has to be multiplied with the first delay element, 11 has to be multiplied with the second delay element, minus 2 with the third delay element. So I'm just looking into the transfer function, this complete transfer function I am trying to plot. Okay, so this transfer function, looking into this particular transfer function, I can directly plot what? I can directly plot this what we call it as the direct form 1 structure. Okay, then what we have to do? Yes, coming back to the poles here, the poles here, the direction of the pole, that is the here, it is towards x of n, that is in the opposite direction. That's the reason we are trying to change the what? Change the sign of your what? The multiplying factors, that is your 5 by 4 is being changed with what? Here it is a minus sign in the transfer function, but here it is a plus sign. Why? Because the direction here, it is in the opposite direction. Okay, that is the direction here, it is moving from what? Y of n to x of n. Okay, from here it is direction is something like this. Okay, that is from x of n towards your y of n itself. But here what is happening? Here it is in the opposite direction. So the thing is, we have to change the direction, that is the change the sign change, only the sign is being changed in the structure. Okay, so but we have one of the what we call it as a disadvantage in this particular type of your structure. What is the disadvantage here? The simple disadvantage what we can see in this particular type of your structure is the number of delay elements what we are required, or the memory element what we have required is twice of your order of the filter, or the twice of the order of your transfer function. Okay, to overcome this type of your what we call it as a delay, or overcome to this disadvantage, We are trying to go for your direct form two structures. Okay, so yes, once we are done with your direct form one structure, we have seen the disadvantage in the direct form one structure. That is, the main disadvantage in the direct form one structure was, that is, the number of delay elements required or the hardware components for the implementation required will becoming double of the order of the filter. Okay, so to eliminate this, we have one more structure, that is the direct form 2 structure. In the direct form 2 structure, what we are trying to do is, that is, we are trying to combine the number of delay elements required for the poles and as well as for the zeros as same. That is, instead of twice, we are trying to reduce it to one. So depending upon the order, the same number of delay elements will be required for both the poles and as well as for the zeros. Okay, and of course, for bringing down this into a form of a direct form structure, we have a shortcut method. But instead of going into the shortcut method, first I will teach you how to get the structure in a form of a mathematical expressions, or we call it as an equations. Then it is better to go with your shortcut structure. Okay, so what we have to do here is simple thing, that is, the given transfer function h of z, I am trying to decompose into two products. The two products here, I'm calling it as my h of z. I'm segregating into two products, calling it as h1 of z and h2 of z. What is this h1 of z? That is, I'm calling it all the poles as separately as h1 of z and zeros as my h2 of z. That is, all my poles as my h1 of z and all my zeros as my h2 of z. So we know that the poles are nothing but in the transfer function which is lying in my denominator. The poles are in the denominator, the zeros are in the numerator. So when I'm taking out my transfer function, dividing into two parts, so my h1 and h2 of z, I'm taking first the poles, but I cannot directly take the denominator. Means I am trying to take only the denominator part. In the denominator part means leaving out the numerator part aside. So I can write down my h1 of z as what? 1 over, for the same numerical, it is 1 over 1 minus 5 by 4 z inverse plus 3 by 4 into z to the power of minus 2 minus 1 by 8 into z to the power of minus 3. Okay, so you can see for the same transfer function, this is the transfer function. For the same transfer function, I'm trying to write in a form of a direct form 2 structure. Okay, so what I've done now, the first thing is I've returned segregated into H1 and H2, that is poles and zeros separately. So the poles I'm calling it as H1 and zeros I'm calling it as H2. And in the poles, I got the expression as what? 1 over 1 minus this complete term. Okay. And what I'm trying to do here is, when I'm trying to segregate this, that is, in the input, we have x of n. At the output, we have y of n. In between h1 and h2 of z, I'm bringing down one more term, calling it as v of n. Okay, so I can write my expression here with the two different transfer functions here. So output for my h1 of z will be v of n, and input for h1 of z is x of n. Similarly, for h2 of z, input is v of n and output is y of n. Okay, so my v of n is acting like input for h2 of z and output for my what? H1 of z. Okay, so what we are getting here is, I'm trying to write down the same expression in a form of v of z here. So what will my v of z will become now? So v of z is nothing but so my v of z, which is equal to x of z into my h1 of z. Okay, so my h1 of z will now become what? My h1 of z, that is nothing but I can represent the both the h1 of z and h2 of z in a form of a transfer functions. So for my h1 of z, output is V of n and input is X of n. For H2 of Z, output is Y of n and input is V of n. So if I write my transfer function as H1 of Z, which can be written as what? Output by input. So output is V of n by X of n. The same thing I have written here in terms of a Z terms. So my V of Z will becomes what? Now V of Z is equal to X of Z into H1 of Z. Okay. So this is nothing but V of Z is equal to X of Z into H1 of Z is the transfer function what we have got in the, from the numerical. This is the transfer function. Then multiplying this, we'll be getting V of Z is minus 5 by 4 Z inverse into V of Z plus 3 by 4 Z to the power of minus 2 into V of Z. Of course, minus 1 by 8 into Z to the power of minus 3 into what? V of Z, that is Z to the power of minus 3. Missed out V of Z here. Okay, please, you can take down. So yes, V of Z into minus 5 by 4 Z inverse V of Z plus 3 by 4 Z to the power of Z square into V of Z. And of course, there is V of Z here also, that is minus 1 by 8 Z to the power of minus 3 into V of Z, which is equal to X of Z, which is equal to what? X of Z. Okay. And this term I'm trying to write in terms of a n term, so which will become what? V of n. I'm trying to write down in a form expression in terms of V of n itself. So my that is output itself. So V of n will become 5 by 4 into X of n minus 1. So Z inverse now I can replace with what? X of n minus 1. Z to the power of minus 2 as what? V of n minus 2. Everything I'm replacing instead of what? Instead of Z inverse by V term itself. So it is V of n minus 1, then V of n minus 2, then V of n minus 3 plus your X of Z as X of n. Okay. So the complete term now it will be V of n is equal to 5 by 4 X of n minus 1 minus 3 by 4 into X of n minus 2, that is V of n minus 2 uh, plus 1 by 8 into what? V of n minus 3 plus your X of n. Okay. So everything is here, it is in terms of V. The last term is my X. Okay. Then similarly, considering from the second one, that is your H2 of Z. What I have done with your H2 of Z? For H2 of Z, input is V, output is Y. Okay. And that H2 of Z, I can write down H2 of Z as what? Output by input, output is Y of Z, input is V of Z. So I can write my Y of Z as what? Y of Z is equal to V of Z into H2 of Z. H2 of Z is nothing but only the zero part. Zero part is nothing but only the numerator terms. So the numerator terms are 8 minus 4 Z inverse plus 11 into Z to the power of minus 2 minus 2 into Z to the power of minus 3. Okay. This is what we are getting here. And this taking inverse Z transform, writing down in the form of what? N terms. So my expression will become what? Y of n, which is equal to 8 into V of n minus 4 into V of n minus 1 plus 11 into V of n minus 2 minus 2 into V of n minus 3. So the Z term now I'm replacing with the n terms. So it will become what? N minus 1, n minus 2 and n minus 3. Okay. So we have two expressions now. One for your poles, the other one for your zeros. Okay. And both the expressions is been related with what? The terms V, Y and X itself. Okay. Everything is been related with your V, X and Y itself. If you see in the both the expressions, expression number 1 and expression number 2, we can see the delay elements required is only 3. Why? We can see here it is 5 by 4 into V of n minus 1, 3 by 4 into V of n minus 2 and 1 by 8 into V of n minus 3 in the first expression. In the second expression, that is minus 4 into V of n minus 1 plus 11 into n minus 2 and minus 2V into n minus 3. So the number of delay element required has now reduced into only the 3 compared with your direct form 1 structure. So what is the first step we have to do? Write down this line, that is direct form structure. I'm writing down on the same thing, rewriting on the same thing. Okay. Yes. The first thing is straight line relating between what? X of n, V of n and Y of n. Okay, so we have an x of n at the input, in between v of y of n, and at the output v of y of n. Okay, the next term I'm trying to write, that is separately equation number 1 and equation number 2 separately. In the equation number 1, if you see how my v of n, that is related, my v of n is equal to, that is this v of n is equal to 5 by 4 into v of n minus 1. So I'm just trying to take the delay elements. That is, we need 3 delay elements. That is, of course, that is, this is the first delay element, v of n into that is z inverse, that is, it will become what? At the output of this, it will become v of n minus 1. After the second delay element, it will become v of n minus 2. And after the third delay element, it will become v of n minus 3. Okay, so I'm just taking the third one once again here. So we have three delay elements which has been taken here. Then how to write down the remaining parts? It is 5 by 4 which has to be multiplied by 5 by 4. My v of n is equal to 5 by 4 into v of n minus 1. So 5 by 4 into the summing point. I can write a summing point here. I can write a summing point here, and I can write a summing point here also. Okay. Yes, it is 5 by 4 into v of n minus 1, then minus 3 by 4 into v of n minus 2, then plus 1 by 8 into v of n minus 3. That is with respect to the first expression. Okay. What about my second expression? In the second expression, it is, I'm trying to write in terms of what? Y of n now. Okay. So my y of n will become what? 8 into v of n, of course, 8 as it is, into v of n, then minus 4 into v of n minus 1. V of n minus 1 is here, which has to be multiplied with minus 4, of course, minus 4. And I can write a summing point at the end. Okay. Then minus, that is plus 11 into v of n minus 2. I can write a summing point here, summing point. Okay, that will become v of n minus 2 into 11, then minus 2 into v of n minus 3. Okay, so if you just compare with your direct form 1 structure and the direct form 2 structure, in the direct form 1 structure, the number of delay elements required was doubled, but when it comes to the direct form 2 structure, the number of delay element required is the same as the order of the filter or the order of the transfer function. That's the reason the direct form 2 structures is being used for the remaining structures, that is for your parallel structure and as well as for your cascading structures. Yes, coming down to the second numerical here, yes, the given transfer function which was given h of z has been given. By simplifying both the numerators and the denominator, then dividing by with your highest order. The highest order is nothing but it is the 4, z to the power of 4. I can finally obtain my transfer function in the form of with the delay elements, that is y of z by x of z, which we will get in the form of 1 minus 2 z inverse minus z to the power of minus 2 plus 2 into z to the power of minus 3 divided by 1 minus z inverse plus 9 by 16 z to the power of minus 2 minus 1 by 16 z to the power of minus 3 plus 1 by 32 into z to the power of minus 4. So if we just see here, the number of delay elements required for the poles and required for the zeros is getting separated. So the number of that is the delay elements required for the poles, it is 4, and the number of delay elements required for the zeros is 3 itself. Okay, writing down in the form of a direct form 1 structure, I can directly write down the direct form 1 structure with the 3 delay elements for your zeros. So 1, 2, 3 delay elements for the zeros and 4 delay elements for your what? For your poles. So 1 to actually we can write a delay element here. I missed the delay element here. Please write down the delay element. Okay, so delay element here and delay element here and one more delay element here. Okay, 3 delay elements has to be returned, that is totally 4 delay elements. Then what is the next thing we have to do once we write the delay elements? Then for the poles, for first we can write down for the zeros, there is no sign change. As it is, we have to write, that is 1 with a multiplying factor of 1, then -2. Looking into the transfer function, I'm just looking into the transfer function here. This is my transfer function. Okay, in this particular transfer function, I'm just looking for the poles and the zeros. The zeros is nothing but the numerator terms. So in the numerator, what are the terms? We have 1, -2, -1, and 2 plus 2. Okay, that's it. When it comes to the poles, of course, for the poles, the direction has to be changed. So that's the reason. That is nothing but what has happened now. What has happened, if you see here, in the direct form 1 structure, there is a change in the sign of your poles. So what will happen? It will become -1, +1, minus 9 by 16, plus 1 by 16, and minus 1 by 32. Okay, so looking into the transfer function, we can write zeros as it is, poles with the change in the sign. When it comes to the direct form 2 structure, first we have to write the poles, then with the zeros. Okay, first with the poles, then with the zeros, and the change with the poles. Okay, that is a sign change with the poles, and there is no sign change with your zeros. Okay, so direct form, writing down the direct form 1 and 2 structure is really a simple thing.